Labguy here. Just a quick update for you. This is episode 12 of the PhiloCam series. Construction is underway on the deflection board for the camera, and as usual, parts are in the mail. So we're kind of at an impasse at the moment. I don't dare proceed to keep assembling the board and end up painting myself into a corner. I'm waiting for a pulse transformer, which I will cover in just a little bit. So at the current state of things, I want to touch on the sync generator board and show you the final schematic at this point. There are two significant differences since the last time I showed it to you. The first is a simple one. The memory chip enable signal, which I was going to generate with the state machine, is now simply the composite blanking output run through an inverter chip. As I looked at the memory chip enable signal, it was obviously the inversion of the blanking signal, so it was that simple. The other change was that I built two ramp generators, an X ramp generator and a Y ramp generator, right onto the board, so that we can easily connect an oscilloscope to the board for probing the camera, and it will produce scan waveforms so that the oscilloscope becomes a picture scope so that we can probe around in the video path to see what is going on in that when we get to that stage. Let's look at that full page schematic now. If you want to study it in detail, go ahead and hit your pause button. So the next schematic that I've been working on, of course, is the deflection board schematic, and it contains the horizontal scan and the vertical scan. So this is what it looks like in its entirety. So now let's take a closer look at the horizontal scan circuit. In that, you'll see that there is a pulse transformer again driving the base of the HOT, the horizontal output transistor. The input of the pulse transformer is a pair of FET switches being driven by a drive square wave, once again coming from the state machine memory chip. Now, in the current phase that it is in phase with the blanking. The scanning waveform on the camera tube will probably be offset to one side, something like that. So in the future, once it's running, I can move the waveform in the memory to bring the picture to the center, and it will be centered in the tube, even though the scan will be goofy. It'll be asymmetrical, but that doesn't matter. We're only concerned with what is in the active picture region, as you saw in the previous video about the active picture region of the memory. The camera tube will be centered up into that as well. The scan circuit is very similar. It's almost identical to the scan circuit from the Chief, and so it has it drives the deflection yoke directly and has a simple voltage regulator on the top end of the yoke on the positive side, which we adjust the voltage to scale the width of the picture, of the width of the scanning. In a camera, if you make the scanning smaller, the picture on the monitor gets bigger, and vice versa. Just a trivia thing for you. So that covers the horizontal scanning circuit. Now when we look at the vertical scan circuit, if it doesn't look familiar to you, it's because you haven't watched the series about the Chief. This scan circuit is exactly the same for all practical purposes. There will be some resistor value changes and a capacitor value change to make it scan at 15 cycles per second and scan a raster this big instead of that big. Let's look at the schematic you've all been waiting to see, and that is the schematic of what it takes to fire up an image dissector tube. One, the burning question in your mind is, what does an image dissector tube schematic symbol look like? And two, how hard is it to make it work? Well, put your peepers right there. So if we look closer at that circuit, you can see that it is simply a voltage divider driven by a high voltage power supply. Moving left to right, we are going from the most negative terminal to the most positive. The output end of the tube is at ground potential and is terminated into a 100K resistor on this schematic. We'll find out what the real value is as we debug the system and make it work. Looking at the symbol of the tube, the far left side is the photocathode, and it is connected to a variable resistor which allows us to vary the voltage by about either 500 volts or 1,000 volts. I can't see it from here, so I'm not going to guess. And embarrass myself again with bad numbers. If you guys paid attention in the last video, there was a lot of bad numbers. So back to the schematic. The second adjustment, the second resistor in the chain is another variable resistor which adjusts the voltage of the first dynode. Those, 9 diagonal lines in the left hand of the symbol represent the dynodes inside the tube, the electron multiplier. And as they proceed from left to right, they become more and more positive by approximately 100 volts. Now this can change depending on the setting of the pots. The final pot really sets the entire current of the chain and can kind of move the voltage on the dynodes kind of like an accordion, where they can be maybe 80 volts apart up to 110 volts apart, but generally that's what that control will do, and set the gain of the dynode chain. Between the photocathode and the dynodes is the drift tube, and I've drawn it with a dotted line on the left side representing a screen mesh, which I believe is present inside this tube, same as in a Vidicon tube. The screen mesh has a collimating effect to really get the field of electrons from the phototarget to really line up parallel as they travel towards the back of the drift tube. Remember, they're sitting inside of a magnetic field that runs the length of the tube and acts as a collimator like you would have in a laser, and so that the rays are parallel to each other. So the next thing I want to touch on is the pulse transformer for the horizontal scan is a surplus item coming from one of my favorite online surplus stores, Electronic Gold Mine. And I believe it's a transformer designed for Ethernet interface for power over Ethernet. That's why it has a center tapped winding. And I'm going to use the center tap this time to do the biphase drive to the base of the horizontal output transistor. Then in terms of the physical construction of the project, I have removed the high voltage power supply from the box, and we'll be reworking this slightly and pretty much stripped out everything that was in here, and I've taken the deflection yoke out and rotated it 90 degrees. It came from the exact same kind of slow scan camera as I showed several episodes previously, in which the fast scanning of that deflection system, the scan lines were vertical. Well, we don't want vertical scan lines. We want them horizontal like in a normal TV. And so I had to do a little rework to rotate it because the 4 screw holes on the front are not in a square. Needless to say, nothing comes easy. Once again, this was a Vidicon deflection yoke with the image dissector tube in here. I've created a small wiring harness with a plug, which will plug into the deflection board, which is already under construction, and the deflection board will sit here, and that plug will plug onto the lowest of the 3 connectors on the end. I thought it was kind of cute to put all of these TO220 packaged parts all in a nice straight line and line them up. This one is the focus current regulator, which I didn't cover. These 2 are the vertical output transistors. This is the horizontal output transistor. This is the horizontal size voltage regulator, and this one is the 5-volt voltage regulator for the inverter chips. So far that comprises everything to drive the deflection yoke, including the focus coil, horizontal and vertical deflection. And for the curious, the fully decked out sync generator board in its entirety looks like this. It has all of its chips in place, the voltage regulators over here, and this is a fully functional standalone board now. Will drive the PhiloCam monitor as you saw in the previous video. So that is the current state of the PhiloCam project. I know this video wasn't filled with exciting images of things running, but at the same time it's been a few days and I don't want to leave my viewers hanging, so I thought I'd bring you up to date on that. If you liked the video, and I hope you did, please click the thumbs up button. Not enough of you are clicking the thumbs up button. It's possible you're not making it to this point in the video. Well, that's life. Tell a friend. Thank you for coming to see this video, and keep coming back as this project progresses. It should be making pictures here within a week or 2. Let's keep our fingers crossed that all the parts come in on time and that the circuits work as calculated. So until next time, this is Labguy out.